Hello, thank you for joining today's presentation, Techniques for Rapid and Accurate Sample Analysis in the Field, Setting the Industry Standard. I'm here today with my colleagues Aaron Bench and Dane Burkett. Thanks for making the time to be here today. As a reminder, please submit questions at any time during the presentation, and we'll field questions from the audience at the conclusion. With that, let's get started, and I'll give a warm welcome to Aaron Bench.
Thanks, Michelle. Good morning, and thanks for joining the webinar. As Michelle said, my name's Aaron Bench. I'm Principal Geologist with International Mining Group here at Olympus, and I'm joined by Dane Burkett, our Portable XRD Product Specialist. So today our webinar is going to address rapid and accurate sample analysis in the field and techniques which we've spent many years basically building up and perfecting here at Olympus. So I'll start with a really quick intro. This is what we're going to run through today. We're going to have a quick introduction to Olympus, our mining team, and what products that Olympus has in this space. We're going to do a quick intro to Portable XRF and Portable XRD principles and how they work. Then we're going to focus on XRF and work through the products, the workflows, some of the suggested operating procedures, and then spend a bit of time looking at good references, case studies, and applications. At that point, I'll hand over to Dane. He's going to do the same thing, but with the XRD product portfolio. So just kicking it off, Olympus has the very proud background of having the world's only dedicated international mining group. It's been the cornerstone of our success in this industry. We have a bunch of geoscientists and environmental scientists who've been working in this sector for over 20 years, so including myself and Dane. So if we have a look at how these products fit into the Olympus portfolio, obviously Olympus is a very big business. Many people are familiar with our consumer products or our medical businesses where it's all around imaging. But our products report to a division called OSA, so Olympus Scientific Solutions Americas. It was part of the non-destructive testing portfolio where we now include X-ray fluorescence and X-ray diffraction for doing chemistry and mineralogy. And for those that remember, it was part of an acquisition called Innovex Systems, where we were acquired by Olympus back in 2010. And what that gives us, we're the only company that has a completely integrated geoscience solution. We have diffraction, which can give us quantitative mineralogy. So if we're looking at this slide on the top left, we can actually derive the minerals and the amount of minerals, so we can quantify them. We have X-ray fluorescence, which is chemistry. We get very good, almost lab-grade results if we're doing the right job. And then we also have the ability to look at structural properties of geoscience as well through microscopy or optical mineralogy or petrology, which is again, it's the backbone of what we learn at university when we're looking at mineralogy. It's the gold standard in a lot of ways. Breaking it down to the products, and again today we're just going to focus on the products, the portable products. This is our XRF products, so again chemistry. We have the new Vanta series handheld, which I'll explain a little bit in the next section. We have the Deltas, which has been the workforce for a good 6 or 7 years now. Many people are familiar with our Delta series handhelds. And then I'm just going to mention we have some portable benchtop, some sort of customized smaller systems, as well as our process and online and sorting systems as well. If you'd like more information about the other products, feel free to get in contact with us after the webinar. And then looking at the diffraction systems, and again, I'm not going to steal much of Dane's thunder. We have two offerings there. We have a portable system called the Terra and the BTX2, which is a small benchtop system. And the one slide which I've got for microscopy is that we have a bunch of solutions from stereo microscopes through the polarizing microscopes and metallurgical microscopes, which are all around optical mineralogy. Again, if you need more information, we can point you to the product managers and the specialists in the microscope business. So what is XRF and XRD? As you would have read in the webinar intro, this talk is essentially targeting people who've got an existing background in the physics. So I'll keep it quite simple, but again, if you need more information about how the fundamentals work, we can provide you with that. So X-ray fluorescence, we shine an X-ray on the sample. We use a technique called EDS, so it's energy dispersive XRF, where basically we get characteristic X-ray lines back for each element. We measure them in a spectra, we quantify them, and that's what we use to get a quantitative result for each element. Diffraction's quite different. We're basically, again, shining an X-ray on a sample. We're looking at diffraction of the mineral lattice or the layers within each compound or crystal structure. and we end up with a diagnostic fingerprint for each mineral, and then we can quantify that using processing techniques, which Dane will spend a lot more time talking about. So as many of you know, the periodic table continues to get better coverage and better sensitivity. We've looked at this many times over the years, and essentially what we're looking at in the green is elements that we can get down to single ppm or low ppm levels. So with modern, high output X-ray tubes and with silicon drift detectors, we can now do a really good job across pretty much the whole periodic table. And especially the light elements. The new systems give us the ability to do things like magnesium, aluminium, silica down to levels that we've not been able to do before. And if we start to look at the market now, we play in quite a few different parts of the industry, what we call the mining value chain. We start with geoscience research, with geological surveys. We then move through mineral exploration from greenfields, first boots on ground, right through to brownfields, where we're developing around existing operations. We then move into the grade control area, where we've got systems which are able to make real-time decisions around materials and destination of materials. From there, we're able to use that to inform the processing division of the business, so around geometallurgy and aspects of decision-making on chemistry and mineralogy. And then at the very back end of the business, we can also play a role in mine closure and in the environmental business around looking at soil remediation, contaminated land. There's one separate business which we have a nice sort of segue into, which is around maintenance. A lot of our tools are used for NDT and for looking at alloys and PMI and things like oil. And again, if you'd like more information on that, which I'm not going to cover today, we can point you in the right direction. So let's delve down a little bit and focus on XRF in particular. And this is where I'd like to just quickly talk about our new offering. So in September, we released our 5th generation handheld called Vanta. It's a complete revolution in the industry. It's 10 plus years of basically building an instrument that's been specifically designed for our market. And when I say that, the core pillars are around ruggedization. So we now have IP67 rating, dust and waterproof. We have very high temperature ratings, up to 50 degrees C, full duty cycle. And one of the cool things is the detector shutter with a mechanical eyelid that can come down and protect the detector. We also have revolutionary called Axon technology, which is all about better accuracy, better precision, and higher count rates, which means we can do more work faster with higher accuracy and higher precision. And in the productivity space, we have a whole bunch of new cool stuff coming around cloud-enabled data processing. We have things like embedded GPS and new software. It's a revolution in handheld XRF. So the product aside, where we've really established ourselves as essentially the industry leaders, is we all know that XRF can do a great job, but there's a bunch of things that we need to do, and it's very similar to what the lab has to do when they process our samples. It's all around best practice. So back in March of this year, we put out a blog, and we had a week called Geoscience Week, where we put out a guide called a quick start guide for best practices in portable XRF. And again, you can go to LinkedIn, go to the blog and pull that down. But I'm going to discuss a few of the points that are in there because these are kind of the critical elements that we need to basically design an effective and rapid portable XRF program. So if we look at the start, we need to start with designing an orientation survey. A lot of that's around standard operating procedure, chain of custody, QA/QC, all things that as geologists we're very, very comfortable with dealing with our normal lab regime. This paper that was published, and I was a co-publisher of in 2014, is a cornerstone paper which goes through each one of these procedures. So around each part of the procedure, around selecting a sample, preparation, what do we want to look at around sample preparation, data handling, data custody, and then what do we actually want to do with the data when we're finished. So there's a great reference there which you can go and look and download. And the next part, it's all about selecting what sample. What are we working with? Are we working with biogeochem samples? Are we working with soils? Are we working around a drill rig where we're taking percussion, or we actually want to look at drill core? So we have to make a decision about the way we're going to analyse that sample and then move forward with the process. And this slide encompasses a few of the really key aspects. Probably the main one in the top right corner is grain size. And we know that if we have homogeneous, good materials, we're going to get a good result. But if we're analysing coarse grain materials, we're going to get very erratic and heterogeneous results. Similarly, if we're running through bags, we're going to get attenuation. That's obviously going to affect the calibration. It's going to dilute our results. So we're able to do that, but we need to make sure that our site-specific calibration is built up to take care of all of those things. And on the left, it's an example of how to actually select the right type of soil to go out and sample. We're looking at a soil horizon here where different parts of the stratigraphy deliver different types of metal due to things like redox and chemical reactions going on in the ground itself. So we're actually able to use portable XRF to tell us what sample has the accumulation of metals and which sample is going to give us the best results. So as the manufacturer, we do the best job we can to give you guys a robust calibration out of the box. You know, we run lots of different standards and lots of different samples, but at the end of the day, you want to make sure that you're qualifying the instrument and you're doing the right thing around looking at the performance of the XRF versus certified reference materials. This is an example of a company, very well known, All Research in Australia, who have very good standards that we can go out, and this shows portable XRF versus lab for iron in this particular case. And if we're doing the right thing, we get the same result. So it's very encouraging. And this shows, this is a set particularly for iron ore, which you can go and buy off the shelf. There's some pricing there. This is the packaging. You basically get a nice little portable XRF standards package you can take out into the field and use as part of that sampling regime. Now, the next step in the process that we're very, very comfortable and very used to doing is coming on site and developing site-specific standards. So we're working with your site-specific standards because the final refinement or the fine-tuning or tweaking it, call it what you will, is actually tailoring the XRF to do the absolute perfect job for the type of rocks that you're working with. And what we can see in the bottom left-hand corner here is this is a set of, I think, about 35 or 40 samples for a very low range of a metal. In this particular example, it's copper and iron in an IOCG deposit. And we build the calibration and basically tweak the calibration so we get a one-to-one reading and a 99% correlation to make sure that you're very confident that the analyzer is doing the right job. As I mentioned earlier, one of the critical points with portable XRF is around sample presentation. And again, we have a whole lot of solutions and a whole lot of expertise around providing guidance and providing recommendations on what sort of tools and equipments that we can use in the field. Again, if you'd like more information, we can certainly point you to the right direction with some of these companies, whether it be drilling a hole in a sample or taking a sample right through a lab-based, a ring mill or a jaw crusher to get 95% of your sample passing 75 micron. The more that we get towards that, the better results we can achieve in the field. And if we just want to spend a few seconds focusing just on field-based sampling solutions, there's some fairly well-known bits of equipment out there which you can go and purchase, including this rock grinder, which you can take a channel sample either across a wall or a face underground, or there's this small hammer mill up on the right-hand side, which we can use for crushing things like RC chips or soil and regolith that's not quite homogeneous enough in the field. You can take these out in the field, run them off a 12-volt system off a car, and quite easily obtain lab-grade results in the field. And then more at the complete solution level, we have a company that we work in tandem with around creating and basically developing a full solution, and that's crushing and grinding. We have a sample press. The sample press enables you to create a puck without a consumable. It doesn't require a window, which means that you're getting a lot better XRF performance without any attenuation. They also have a LIMS system, which for those in the laboratory, it's a laboratory information management system, which manages the chain of custody, the standards. It manages the real-time QA/QC actually while you're running the sample, so it gives you confidence that you're getting good results whilst you're actually running the samples. And a key part of what we're delivering is how do we deliver our data in real time. And anybody that's used a portable XRF knows that we can basically generate a lot of data very, very quickly. We've got spreadsheets of multi-element data arriving all over the place. I quite often see people's laptops where they've got 20 or 30 spreadsheets all together on the one page, and it gets quite difficult. But having solutions like this one I've got up on the screen, the data can arrive into a real-time web portal. It can be QA/QC validated. It can be managed remotely, and then we can get an output which is designed in exactly what the client would like to see. roll out of bed in the morning before they go and see the drill rig, and they can see the data on their iPhone and say, oh, look, we've drilled through the contact, we need to stop the drill and make that decision, save lots of money, and then move the drill to the next spot. It's all about real-time decision making. And then once we have all that data, it's what do we do with it? And as geologists, we generally pass that into a 3D model. We use that 3D model for a lot of things. We use it for mine design. We use it for vectoring towards mineralisation or targeting where we're going to drill next. And we have tools where we have our portable XRF data can arrive into a classification system, as in the right-hand corner there. The rocks get classified and then pass straight into a 3D model. So it's all about expediting the chain of custody of the data that usually can take months, even up to half a year to get this data into a model and start working with it. And then the one small part I'm going to talk about a little bit is about how we take that data and we're actually, how do we report that data to the market? And again, it's been quite controversial in the past, but back in 2012, myself and a few others involved around PXRF technology spent some time with the JORC panel and said, well, let's include some of these sampling techniques, some of the recommended procedures when people want to report the data. So we can go to table 1, we can get some information, and we can get some recommendations on what we need to do to report it. Again, for those who'd like more information, we've got lots of good examples of companies who do this the right way and what you should be looking at to put out in the market. So one of the very well-known industry initiatives that happened a couple of years ago in 2010 and 2013 was the CAMIRO project, which was staged up here. I'm sitting in Boston, so up here in Canada, run by Gwendy Hall, who's a very well-known geochemist, where we had a bunch of industry companies who sponsored, and we worked through the quality control and assessment of portable XRF. It was all around benchmarking. What can XRF do? How can we develop standard operating procedures on variable media? And how can we recommend the best use? So again, that's a great reference. I think there's about 500 pages of reports and data there, and you can go to it's actually on the Association of Applied Geochemists website and download those reports as a great reference. And as part of that work, Gwendy, who is also the editor of Geo magazine, we put together a thematic set, so 2 complete issues of Geo, which were completely dedicated to portable XRF. And that was where companies or institutions submitted papers on best practice and what they'd done. So it's a great reference out there for those who are looking for papers and for direction on where to head. So moving forward, I'd like to spend a little bit of time looking at some examples and case studies, because today's presentation is really about what you can do with portable XRF and what the industry has been up to for the last 10 or 15 years, because it's become a very well adopted industry standard technique now. So in this slide, I'm just highlighting, we ran a short course for PDAC in 2016. We videoed all of them, so this was a whole day, each presentation is about half an hour, and we invited industry experts from exploration, from mining, from universities, from various organisations around the world to come and present on their experience. And it's been a fantastic assembly of presentations. It's up there on YouTube. There's about 8 hours worth of video that you can sit down and watch and listen to people's experiences. So I'm going to walk through a few of those. So I'm going to start from the start of the mining value chain, which is, for us, it's that academic and geological surveys and kind of the front-end teaching. And this is an example with GTK up in Finland. They've put together a special report a few years back, which has a whole chapter on portable XRF. And for this particular example, it was looking at till geochemistry and how they're effectively using portable XRF to do that. And in line with that, and actually many years ago, about 15 years ago, this is an example of the Geological Survey of Canada, where they were using a similar technique. They're using lithogeochemistry, so using the chemistry to tell us what part of the stratigraphy and what rock types are in. And what we're looking at here on this downhole plot is the blue data is ICP, that's lab data, and the red data is XRF, and we're getting very agreeable results between the 2 data sets. And from there, they're able to work out the rock type, determine the stratigraphy, and basically adapt and design their drill program in real time. So moving forward, and an organisation that we work with a lot in Australia, kind of at the coalface and the cutting edge of PXRF technology, is that we know the data is very, very good. And when we look at these plots, we can see extremely good agreement between elements, which in geoscience, we use certain elements to tell us certain things. We use arsenic as a very strong proxy for gold mineralisation. We use things like titanium, zirconium and chrome, so our mobile to mobile element ratios to tell us what our rock types are. And if we take that data forward, we're actually able to use that to start to predict and work out what rock types are and take the subjectivity and some of the fuzziness out of logging rocks. And what we're looking at here is it's an advanced algorithm. It's actually called wavelet tessellation, where we're using iron through a project that was developed through June Hill's group in the DETCRC, which is a large research initiative in Australia. And we can use iron through a wavelet tessellation to basically break out the rocks into lithology and start to break it down into different scales of features that we're seeing, first order versus second order versus third order features, and to help that and assist us in breaking up the rock types, which may not be visually obvious or difficult to pick out in the field. So moving from the R&D and the geoscience or geosurvey applications is the first place that we encounter XRF in our business is generally around soil sampling. So soil sampling works very, very well. We have fine-grained samples. We're able to move about on the surface of the Earth and map geochemistry very, very rapidly. And in this particular example, a colleague and I, in about, I think 5 or 6 hours, we managed to cover this area at a 50 by 50 grid and basically build up a real-time geochemical map very rapidly. And from there, we could move around, we could decide where we're going to go next, and we can use that as a decision-making tool on how we're going to change our sampling program on the fly. One of the really cool things about having portable XRF in the field is you don't just get one element. In the last example, we were just seeing copper, but now in this particular example, which is the same data set, we can see every element side by side. So we have copper, lead, zinc, and we get to see the way the different metals are moving around in the system, and we can see what's mobile, what's not. We can see contamination overprint. If we're working in an area around a mine, we can see where there's sulfur and sulfides that have been delivered, around roads and things like that. And if we start to talk about the return on investment and what we can actually get out of portable XRF, or the value proposition, the current example I have up on the screen was one of the first users in Australia and shows what can be achieved with 1 month with one instrument. And in this particular example, they were able to go out and do very detailed, very fine geochemical sampling over a known area of mineralisation in South Australia, around the Burra copper deposits, which is one of the biggest copper deposits in the world, and delineate exactly where they were going to go and drill next. And again, this is several years ago as the technology was emerging, and it got the company into the place that they needed to make those decisions. As we move further down the value chain, once we have an anomaly, once we have a target, the first thing we're going to go is start drilling it. And some of the early drill procedures we might use or techniques will be things like RAB or RC. We may use air core. In this particular example, we're using auger drilling in West Africa. We can see the samples are being brought into a benchtop system. We've got a small little XRF mounted in a hood. The samples are being run in very good chain of custody with great validation, and then we're using that data to classify the rock types, because in that area we can't actually tell what the geology is. That we're in an area of residual regolith where basically the weathered rock comes right through to the surface. And in this example, we can actually map out the greenstone belts in amongst the sediments, and then we know where to go and target because we're looking for orogenic gold. So it's a very, very powerful tool for delimiting the stratigraphy through what would usually be very difficult to look at. And sticking on the gold theme, the next example I have up on the screen here gives us an example of what the geochemical signatures and what the common pathfinders are that we're going to use for going out and looking for gold. And one of the things we'll state up front, and we have for many years, is that portable XRF is not very good for gold, but there's a whole host of elements which we can use to go and look for gold, which we term pathfinders. And in this example at the top here, we can see one of those elements with ICP versus the same element with portable XRF, and we're getting exactly the same map, which means that we're very confident that portable XRF is doing the same job. There's a little bit of a gold theme here, and that's because the gold business to us has been, it's been a very effective place that we've obviously put a lot of instruments into, and it's also an application which we've developed a lot of tools and techniques. And this particular paper, which I now have up on the screen, was an example several years ago. A fellow called Mike Gasley in Australia, who put together a program at Plutonic Gold Mine to basically define stratigraphy and use it for geometallurgical work, which we're going to have a look at a couple of slides on the next page. So basically, Michael was able to reconstruct the stratigraphic model around plutonic. Basically, it's a sequence of thick basalts where the basalt flow interfaces, so in between flows, the gold deposits along those surfaces and substrates, which in the top corner are the red circles. We're looking at chrome versus gold, so as we step down the stratigraphy, the gold basically accumulates on the stratigraphic boundaries. We're then able to do 3D iso surfaces of that, where we can actually model that, and then that uses it as a tool for vectoring and for modelling where we think the next gold occurrence is going to be, or look for extensions of the ore body. He was also able to take that data and domain it out in a deposit that's quite difficult. It's a refractory gold deposit. It's got high arsenic. It's got free milling gold versus refractory gold. Essentially, as the arsenic grade goes up, the recovery drops. So what they were able to do was blend and change the processing technology so they could optimise recovery based on the material that was being delivered to the mill. And again, it's an excellent example of having a data set which they didn't have in the past to drive better recoveries and get better results in the mill. One of the other cool things we've added in the last few years is the camera and collimator feature. And what that gives you the ability to do is actually use the XRF with a focusing mechanism, so it's using the camera. We can collimate down, so we can change the size of the beam to look at smaller things, and we can actually use that for doing microstructural assessment or looking at grain particular or phase particular work. So we have some pyrites and tourmalines and gold grains in these particular examples, which were quite difficult to observe by the eye, but with an XRF and a camera we could do a great job. So moving right through to, we're moving into grade control now. We have an example here of iron ore in the northwest Pilbara of Australia, where our new systems have the ability to take something that was once a 90-second test and do it at 15 seconds. So what we've got here is iron essentially in 90 seconds versus 15 seconds, and again silica. This is an example where light elements perform extremely well. And it's hard to believe, even myself, that we can deliver such good data in such rapid time, which means you can put a lot of samples through where you may not have been able to before, and you can make decisions much faster than you've ever been able to before. And on the second side, we're looking at aluminium and phosphorus, looking at the clay contents and looking at the deleterious elements in iron ores. So the last example I have here, it's a very hot topic at the moment. The whole lithium batteries business is obviously very energised at the moment, pardon my pun. And it's a technique where we can actually use portable XRF and XRD together, because if we're looking for lithium, there's a bunch of very cool elements in the periodic table, one being rubidium. It fractions into lithium in the same sort of ratios that we see in lithium. And the other thing that we need to do is look at the mineralogy. So we may have a lithium deposit, but it doesn't necessarily mean we can mine it. So the XRD is a fantastic tool. We're looking at what phase. We can look at whether it's spodumene or if it's pedalite, or if we're looking at clays or micas that have lithium concentrated in them and make those decisions. Which is a great segue to Dane, who I'll hand over to talk about the similar application of portable XRD.
Awesome. Alrighty, so I'm going to be talking to you about, my name's Dane, I'm the XRD product specialist for Olympus, and I'm going to be talking to you today about XRD. So first of all, Aaron's already introduced XRD a little bit. So XRD is X-ray diffraction, and it's a way of defining crystalline phases or minerals. So where XRF may tell you have 10% iron, for instance, XRD will be able to tell you what phases the iron's locked up in. So for instance, magnetite, hematite, for instance. And the benefit of XRD compared to other methods for defining mineralogy is it can identify all mineral phases irrespective of reflectance. So it can do sulfides, it can do feldspars, all silicates, and it can be used to not only identify minerals, but we can use XRD to quantify minerals also. So just basically, how does XRD work? Well, XRD works by firing an X-ray at a sample, and the angles at which the X-ray diffract are indicative of the mineral structure, so much like a fingerprint. So up the top we can see quartz. There's quartz, there's the crystal structure for quartz, and there's the diffraction pattern, and below we can see cuprite. And there's cuprite, there's the crystal structure, and there's the diffraction pattern. And the reason we showed both cuprite and quartz is Cuprite's an example of a mineral which is you would not be able to do with other reflective methods, as it does not reflect light with infrared. So moving on to conventional XRD instruments before we move on to portable XRD instruments. Conventional instruments use a goniometer, which fire X-rays out of one arm. They hit the sample and then diffract off and hit a detector on the other arm, and the tube and detector will scan over to measure the angles of diffraction. They're usually large lab-based pieces of equipment. They're energy intensive, so anywhere between sort of 2 to 4 kilowatts, and they require an external water source. So they really are truly lab-based instruments. In terms of sample preparation for lab-based instruments, typically you use pressed pellets. Your sample needs to be dry, less than 10 micron, approximately 300 milligrams. And with lab-based XRD instruments, they make the assumption of both homogeneous grain size and random orientation. And down below, I've just got some examples where you can see we've got some grain size heterogeneity, and it's affecting the diffractogram. The Debye rings, and we've also got some examples of where we have some preferred orientation effects which are affecting subsequent quantitative analysis. With conventional XRD systems, your sample prep can take anywhere up to 15 minutes, longer if you need to micronize. Obviously, if you've been doing this for a while, your sample preparation will be a bit quicker, but it's still not something that you can do relatively fast. So that being the case, the guys from NASA needed to get XRD onto Mars, but the issues were the conventional XRD instruments were too large, the sample preparation too onerous, and you weren't going to get an astronaut up there to actually calibrate the machine. So that being the case, they needed to develop an XRD which was light and rugged without need for calibrations. And even though MSL Curiosity rover was 900 kilos, the XRD that they've got on board termed ChemMin is only 10 kilos. And this XRD works in quite a different way to the conventional reflective systems in that it uses a transmission-based geometry. And with this, the X-ray is fired at the sample. It transmits through and hits a CCD detector on the other side, which is measuring both X-ray diffraction and X-ray fluorescence. Now, I need to mention the XRF that is on board ChemMin is only qualitative, so it'll tell you you've got a fair bit of calcium present, for instance, but it won't tell you how much in sort of ppm or weight percent. But it can be quite useful when you're actually looking at your diffractogram and trying to rule out or identify what minerals may or may not be present. The benefit to having this fixed tube geometry is the fact that we don't need to do calibrations on the instrument because the geometry is fixed. So that means if you take it out in the field, much in the same way that it's sitting up on Mars, you don't need to be thinking about when you're sending it back for service, etc. So that being the case, we'll move on now to the Olympus XRD instrument. So at Olympus, we're proud to have the world's only portable XRD. The sample prep is rapid and easy, as we're going to go through in a second. The instruments are energy efficient, so they use as much energy as a desktop computer. And we don't need to be getting regular realignment of parts, which means you can have it out in the field without needing to think of when you're going to be sending it back. In terms of the instruments that we've got the BTX, which is 12.5 kilos, and the Terra Portable, which is 14.5 kilos. Both instruments are identical with regards to resolution, sample holder options. The only difference is the Terra is field portable, so you can take it outdoors into harsher environments. In terms of sample preparation, the XRD only requires 15 milligrams of sample. So that gives you the flexibility of being able to bulk sample or do selective sampling, say on an individual crystal or vein. You only just need to give it a quick crush in a sieve and away you go, and we'll talk about more advanced sample preparation techniques in a second. But when we were talking earlier about conventional XRD instruments, we were saying how they recommend powdering, quite fine, so preferably less than 10 microns, but ideally less than 80 microns. And the reason for that is we're rotating the sample in one dimension with a lab-based instrument using reflective geometry. So you want to get it as fine-grained as possible to make sure you've got representative sample. You also want to alleviate grain size and orientation effects that we were talking about earlier. So that's why they recommend going down so fine. Whereas with our XRD instrument, because we're vibrating the crystallites in front of the beam in all orientations, we're eliminating orientation effects, and we also have the equivalent of about a 3 micron grain size at 150 microns. As I mentioned, and Aaron brought up earlier, we've got more advanced field sample preparation methods using the hammer mill that you can see in the top right-hand corner to make sure you get good representative sample. And in terms of the instrument has 4 hours portability, and if you hot swap the batteries, you can obviously get longer than that. And they're field ruggedized, which means you can take it out on the drill rig to be getting answers in real time, or at in the pit or at the mine that you're working in. With regards to our sample holder, as I mentioned earlier, because we're vibrating the sample, we eliminate the need to rotate the tube and detector, which means we don't need to do calibrations, but we also help to eliminate orientation effects by rotating the crystallites in all orientations. With regards to power consumption and maintenance, the instruments use as much energy as a desktop computer, so you don't need to be worrying about where your energy is going to be coming from. And our tube life is very long, so assuming you use the instrument for 6,000 hours a year, the tube has a 6-year tube life, which is great for people out in the field. With regards to what can be achieved with XRD, it can be used for both qualitative and quantitative mineralogical analysis. So you can identify all minerals, like I said before, irrespective of reflectance, at a detection limit of about 1 to 2 weight percent. We'll talk a little bit more about the detection limits in a second. We can also quantify the amount of amorphous content within a sample. So say, for instance, you've got high chrosocolla bearing ores, we can quantify how much amorphous content is present. And we can also look at crystallinity to have a look at fluid rock ratios or temperatures of deposition for the different minerals. With regards to testing procedures, there's no overall significant change with regards to the result of XRD with varying run times. What does vary with differing run times is the levels of detection. So if you are looking for detection limits above 5 weight percent, with simple mineralogy, let's say sort of 2 to 3 phases, this will only take you 2 minutes. Complex, sort of 3 minerals plus, you're looking at about 5 minutes. And if you're coming down to 1 to 2 weight percent, you want to go for about 7 minutes for a simple mineral mixture to about 15 minutes for something more complex. And I've just pulled this slide up here to give you an example. If we're looking at the peak at 10 degrees 2 theta, that peak there is illite or muscovite. Now, for that mineral phase, at 5 minutes, you can't really tell whether that peak at 10 degrees is present or whether it's noise. But once you start to get up to 10, 15 minutes, you can see that it is present compared to the lab-based instrument that's down the bottom in green. So the question of how long to run a sample really depends on what sort of questions you're asking the field, and more importantly, what sort of detection limits you're interested in. Just to illustrate that point, I'm just showing data from 5-minute, 10-minute, 20-minute, and 40-minute runtime. And for this, you can see the quantitative results don't actually differ that much between the different runtimes. But in red, I put down the R-squared for quantities below 5 weight percent, just to show that once you start to get around 5 minutes or lower, your R-squareds do start to drop a little more for those minerals below 5 weight percent. In terms of data processing, there's many different ways that you can process X-ray diffraction data. Here we're just going to talk quickly about semi-quantitative analysis using RIR. So RIR being the reference intensity of ratio. And RIR basically looks at the major peak for a given mineral phase compared to the most abundant mineral phase. And then has a look just at the peak height ratios to work out which is more abundant. And RIR is fine for semi-quantitative analysis, but where you start to get significant peak overlap, you really need to be running with Rietveld analysis, which is a method to do proper quantitative analysis. Rietveld analysis works in a similar way in that you're using database files, but it's able to merge the different reference patterns together. And at the same time, you can refine for different crystallographic parameters, such as the orientation, the width, peak position, etc. So it's a lot more powerful than RIR. There's many software packages available that do Rietveld analysis. At Olympus, we suggest CyraQuant because they've got a much better database for poorly crystalline material, which uses observed reference material. So you get better quantification for that poorly crystalline material, which we often encounter in geology, such as the clays, iron oxides, etc. So there is a little bit of a lag, but what's going to be jumping up on your screen in a second is the comparison of RIR results to Rietveld results for a porphyry copper deposit. So on the image on the left, we have the RIR results for 4 to 9 phases from a porphyry copper deposit. On the right, we have the exact same data set processed using CyraQuant, and you can see that the results are much better on CyraQuant compared to using Rietveld analysis compared to the RIR method. Now, I've pulled up this slide as well just to show that if you were to process your data very quickly, just refining for your peak positions in CyraQuant, you would get pretty good results quickly, but you can massage the results and get better results by doing a few other refinements, which take a little bit longer, but it really comes down to what sort of level of accuracy or precision you're looking for with your data set. Moving now on to some applications and where mineralogy is important. So obviously, as geologists, the main way at the moment that we do mineralogical assessment on site is by doing core logging with a hand lens. Alteration is typically fine grained, so we often rely on colour as a guide, but this can be quite difficult, when you've got very fine grain alteration phases, which we often do. When it comes to petrography is another method, which obviously is popular for identifying, quantifying minerals, but petrography can become difficult, especially, so I'm showing down the bottom a rock that's fine grained, still fine grained under a microscope, and differentiating minerals within the same class, such as carbonates or different phyllosilicates, can be quite difficult to impossible to do under the microscope, and even harder again to quantify. So here we've got an image showing with XRD you go from a powder. From a powder you get a good pattern and you can work out what minerals are present, and then from there you can get good quantitative mineralogical results. For metal exploration, alteration studies are obviously very important to guide or vector towards ore bodies, and they can also help geologists to understand the geological environment in which the minerals are formed. And here we're just showing an image to show how XRD can be integrated into your core logging program. Aside from just having a subjective method such as core logging based on texture, now we can integrate quantitative mineralogical data into there to ask some cool questions like, if we terminated the drill hole early, is there anything there to indicate we should have kept drilling? And if we've got a sulfur anomaly, what minerals is the sulfur actually locked up in, for instance? So now I'm going to move on to a case study which was published in 2015, which was using Olympus XRD compared to a lab-based instrument for quantitative mineralogical assessment to sort of proxy towards gold. Now, on this deposit, mineralogy was important because the gold was quite nuggety in its distribution. At this deposit, as you can see on the right, the core trays, it was just muddy breccias. And it was quite difficult for the geologist to differentiate a muddy breccia associated with mineralisation from just fault gouge optically. So, for instance, you can see in some drill holes that hit 10 grams per tonne, you move slightly away, you're at 0. So they wanted a wall rock proxy to tell them whether they were in an area favourable or unfavourable for mineralisation. In terms of the alteration model that was built up for this, we found we had high temperature minerals such as epidote deeper in the deposit with a high amount of adularia, and then at the top of the deposit, away from mineralisation, the wall rock alteration was dominated by illite without any adularia, and then you had this zone of transition between adularia dominated alteration and illite dominated alteration, and it was at this zone this zone of transition between the two that we found most of the gold popped out. So it was great. We had a really good alteration model, but we wanted to see if we could actually go out and replicate it in the field compared to a lab-based instrument. So on the left in that stratigraphic column, you can see we have the quantitative results of lab XRD on a 4 kilowatt system compared to the Olympus XRD at 40 minutes and 20 minutes. and you can see that visually the geologist's interpretation is not really going to change based on the 40-minute or the 20-minute runtime. And if we have a look on the right, we can see on the x-axis is the results of lab-based instrument, on the y-axis is the 20-minute results, just to show that all the minerals were quantified on the XRD on the portable as well as they were on the lab-based instrument. And as you can see in the bottom right-hand corner, with this adularia versus clay ratio that we put together, the mineralisation was really popping out at a particular concentration of adularia to clays, so we're able to use this as an exploration proxy for gold. But the next question I always get after we show this data is, how did you know the data was reliable? You've compared to a lab-based instrument, but how do you know the results from the lab-based instrument were correct? So what we did is, we did a mass balance to chemistry. On the x-axis is the results of laboratory XRF, and on the y-axis is the results of the mass balance using the mineralogy converted back to chemistry, just to show that the technique matched up. We've been doing a lot of work in the last year on looking at XRD for a whole range of different exploration for a range of different commodities. So we've had APS notes that have come out in the last year for bauxite and gold exploration, but we've also got data sets for graphite, lithium, copper, iron ore, potash, many different commodities. So if you're interested in anything in particular, feel free to send us a message or an email afterwards, and we can have a chat, or we can send you through some data to show you how the results look. I'm just going to show one more example now for graphite. Graphite obviously being a hot commodity at the moment, and being something that is carbon being something that is hard to quantify using any handheld device. With XRD we can quantify the amount of carbon not just locked up in graphite, but also locked up in carbonates, which can be quite important. So up the top we've got the results from LECO in the top and bottom graph on the x-axis, and on the y-axis we have the estimated results estimated from quantitative mineralogy. And what you can see is it's doing an excellent job at quantifying total graphitic carbon, and for carbon as carbonates, it's actually been able to verify where there were false positives on carbon and carbonates in the red box. This was because of a high level amount of iron oxides in the samples, which were giving false positives. So the geo on site was really happy that he was able to verify his lab results using quantitative XRD. Spent a lot of time in the last year looking at XRD for mineral processing. It's a really exciting space for us. Obviously we've got time constraints today, so I can't go into it too much, other than just to mention that XRD can help with comminution, flotation, leaching, a whole different range of mineral processing applications, as well as blending. So if you'd like to have a chat about that at all, please feel free to ask, and we can talk further about this. And I've got coming up on the screen in just a second, XRD for metallurgy, just an app note that was brought out in the last 6 months. I'm happy to send this through and have a chat. So without further ado, I'll pass it across to Aaron to wrap up, looking at the future of combining XRF and XRD.
Thanks, Dane. So in the last minute, I'd just like to quickly run through one of the cool things that you're able to do is actually start to combine portable XRD and portable XRF together. One of the great examples that we've published quite recently, and it's a lot of people have probably seen, is the ability to use them together for logging drill holes. And again, without going into too much detail, on the left we can see we're basically deriving quantitative mineralogy down hole. In the middle of this plot, we're seeing various elements. Some are giving us ideas about rock types, some are giving us ideas about the type of mineralisation. And then on the right, we've got a bunch of derived data products where we're using advanced algorithms to determine rock type and determine the fertility of the ore body that we're in, and even back out things like petrophysics, which we haven't been able to do before. This is, it's quite an exciting data set, and it's kind of what I keep referring to as the geologist's drill hole log of the future. And again, if you'd like more information, there was a paper published in Explore magazine through Association of Applied Geochemists back in 2014, and we can point you where to go to get a hold of that publication if you'd like it. And I think I'll leave it on that note. Thanks for your attendance.
Thanks, Aaron. So at this point, we're going to take some questions from the audience. Please feel free to submit questions at any time. The first question we have is here for Aaron. So as you mentioned, portable XRF doesn't work well for gold, but you can use gold pathfinders. So which element would you use to look for gold?
So this is one we get a lot. It's been one of the applications we've had a lot of success with, and for those geologists that have worked particularly in various gold deposits, it's the hydrothermal fluids when they come in, particularly in orogenic and in epithermal or high sulfidation systems. They generally have different elements that come along with them, and I mean arsenic is probably the silver bullet if we were to pick one. Is that we get very strong association in some ore bodies, obviously not all, where we can basically use arsenic at a ratio. To give us a ballpark relatively, not always absolute, of the gold grade. And we have many examples, and there's many published examples that show how well that can work. Yeah.
Thanks, Aaron. So we have another question here for Dane. And the question is, what is the minimum amount of sample that can be analyzed with XRD?
Cool. So the maximum amount that can be done is 15 milligrams, but you can go as low as sort of 5 to 8 milligrams with our instrument. Which, like I said before, is great if you want to do selective sampling as well as bulk sampling, because you can really narrow down and get quite a small amount of samples. So 5 to 8 milligrams is sort of the minimum.
Excellent, thank you. So, Aaron, is there anything else you'd like to add before we wrap things up for today?
I think I just put it out there that obviously there's been a lot of work going on in this space, and that the key to getting good results is not just the analyzer. Is that there's obviously plenty of offerings out there in the market, and the key is actually all the things that we suggested today. It's selecting the right sample, it's using the right sample preparation, it's optimising your analyzer with your rock types. Geology is the term I use, infinitely variable, and it's one of the applications that really pushes our team here in Boston. To keep working on getting better sensitivity, better accuracy, and beyond that is how we take that data and turn it into decision-making products. It's all good and well having 35 elements arriving at one time in front of you on a spreadsheet, but actually deciphering that and making something out of it is a different story. So in the future, look forward to seeing a lot of really cool data products, particularly the cloud, particularly with a lot of mobile devices where we can use these in the field and make real-time decisions.
Excellent. Thanks, Aaron. Dane, is there anything you'd like to a closing note?
I'd just like to say, if you've got any questions about anything today, or there's any applications in particular you're interested in, it'd be great to hear from anyone out there. Like I said before, we've got data sets for a range of different commodities, and maybe you're dealing on something that we haven't really worked with yet. So it'd be great to hear from you. And if you got any questions or you want to talk about a particular commodity, it'd be great to have a chat.
All right. Well, thank you, Aaron. Thank you, Dane. That's all the time we have for today. So if we do not get to your question, we'll follow up by email. We'll definitely send a follow-up email with a link to the recording and slides and some of the other resources that we mentioned throughout the presentation. Again, thank you for your time and attendance. And also we had someone that requested a list of the references for the presentation, and we'd be happy to share that for all the data points listed. And that's it. So thank you very much. We appreciate your time and effort on behalf of Olympus. Thank you.